Hi, to begin today, I'd like you to consider each of these four functions and sketch them on the same set of axes like I've drawn here. Please pause the video, give this a go. Okay, first function is the classic exponential e to the x. Now, we know that it goes through the y-axis at 1 because that's e to the 0. And what is happening then is it just goes off really quickly to infinity. But don't forget this negative tail, it kind of carries on and actually it goes to 0 in this direction. So that one is y equals e to the x. It just keeps getting larger and larger. E to the minus x, actually, probably the easiest way of seeing this one, is the fact that if you were to call this one f of x, then this one's actually f of minus x, which means it's a reflection in the y-axis. Something like that. Of course, we can think about it in its own terms as well. When x gets big now, we're going to get e to the minus of a large number. That's why it goes to 0. And when x becomes negative and large, it's going to get really big. How about e to the x squared? Now this is a different function. You probably haven't ever sketched this one before, so this one you need to take a bit more time. Well, if we look at 0 again, we can see it's still going to go through 0. And then what's going to happen when x gets big? It's going to get big even quicker than e to the x does. So it's definitely going to go off to infinity even more quickly. So maybe I put a little line up here. But when x is small, if I have like 0.1 squared, it's going to be 0.001. Actually, it's going to take a bit more time to go to grow to start with. So it's actually going to look like this. Something like that anyway. And they're all going to cross at, it's going to cross at 1, 1. If you look at e to the x squared in the negative, well actually it's going to have a symmetry going on. Just like x squared has a symmetry, we're going to get the same symmetry here. So it's going to end up going again to infinity more quickly. But maybe something a bit like that. I'll draw it, it's quite tough to compare because I don't think I've quite drawn them. Maybe I should make it go down a bit more like that. Okay, gonna give that one more go. The whole thing. So I know it's going to infinity quicker. Okay, so a little bit like that, I suppose. So not exactly like x squared, but actually it has that kind of shape going on. And finally, e to the minus x squared. Well, again, this one is going to cross at 0, but now what's going to happen? It's actually going to go to 0 in both directions. So it's going to end up here and it's going to end up here. This is always a classic thing to do when you're sketching a graph you've never seen. Think about what happens when x is 0. Think about what happens when x is large in both directions. And then somehow it's going to join up. And now you can just sort of make a rough kind of guess at it, or prediction anyway. But I do think actually it's going to again cross when x is 1. It's going to be the same as e to the minus x. So it is actually going to cross, and I think it's actually going to go above it. Just like e to the x squared goes below it, this one will go above. You actually get this kind of curve. To be fair, I'm not too worried about whether you got it to cross or not, but I was hoping that you'd think about the general shape. I'm just going to show you the exact answer now, just to compare. This is what it is. So actually, I wasn't far out. It's quite hard to do it by hand. The green one's pretty good. This kind of behavior around here is quite tough to get spot on because you got to get the gradient spot on and everything. But those are the graphs, and that's a nice little start to the lesson. My second starting question for the day is as shown. Find an approximation to this integral using the trapezium rule with 4 intervals. So instead of integrating with respect to x, I'm integrating with respect to z, but that's okay, there's nothing wrong with that. I've got an exponential, but it's e to the minus z squared over 2, and I'm asking you to divide by this 1 over the square root of 2 pi. All will become clear why I'm asking you to do this. Just for now, kind of just see it as a bit of practice of using the trapezium rule. Pause the video or carry on watching if you're not sure and you need a few little hints. First hint is that you need to remember what the trapezium rule is, but it is given in the formula book. Here it is. Now we're being asked for the trapezium rule with 4 intervals, so actually I'd probably take that formula and just change it so that it's got n is 4 in there. So it's going to be y0 plus y4, and then 2 lots of the rest. And h is going to equal 2 minus 1 over 4, so it's actually going to equal 0.25. Now what we can do, actually before I do it, I'm going to show you what was going on here. So we've got a function that is very similar to that e to the minus x squared that I drew before. There's actually 2 scale factors going on. There's going to be a stretch in the x direction and a stretch in the y direction. Not too worried about that, but there is a reason why I've put that in. And what we're actually finding is this here, okay, this shaded area, and we split it into these 4 intervals. Just reminding you about that. And then to figure this out, probably the easiest thing, actually I already did it a minute ago, let me do it again from scratch, is to use the table function to get all your values. So it's up to you. You can either do e to the minus x squared over 2 and then divide by root 2 pi, or you can just go the full thing and just include it from the start. Both will give you the same answer. Okay, so be careful you get it on the right line. And your calculator always deals with x, but that's okay. Okay, ignore the second function. We're starting at 1, we're ending at 2, going up in 0.25s, and we get our values that we need. Now I looked at this and it seems like we can't, the calculator doesn't like to store those, which I found very strange, so you end up actually having to write them down. And here are some I wrote earlier. So if x is 1, we get this as the value. Yeah, you can see that they are the same. I'm just speeding up the process for the purposes of this video. And this, if I write next to it, this is going to be y0, y1, y2, y3, and y4. So I can now just substitute that in. I just realized I've missed something out though. I missed the 0.25 out from the original formula. Hopefully you spotted that. Should have been in here, because I hadn't actually calculated h at the time, but that's going to be my full formula. So now that's going to become, well, let me rewrite it as a half times 0.25, and then in brackets it's going to be this 0.2419 plus 0.0539, and then 2 lots of the rest. I'm not going to write it all out actually, like you can see it's 2 lots of these added together. And what we actually get, and I hope you managed to get this, is the following, 0.1366. Now remember that, because that is going to come back in later on. But what we've done, sorry, I was going to end my video, but what we've done there, therefore, is we've actually taken this e to the minus x squared, and we've used the trapezium rule. We've done an integration to approximately find the area. It doesn't look bad, okay? It's not going to be perfect because we're using straight lines to represent it, but actually it turns out to be a pretty good estimate. With this is a bit dodgy, I think. I think this is correct to this 3rd decimal place anyway. Let's get on with the main part of the lesson then. So I want you to look at these 4 plots and think, how would you describe each of them? Are there any similarities? Are there any differences? Well, we look just above, it looks an awful lot like that, doesn't it? It kind of looks like I could fit that strange exponential curve to it pretty well. Oh, and this one. And maybe this one, although you can't see all the data. And, oh, well, maybe not so much this one because it has more of a tail. And here, maybe even going this way, I've got a lot of people that have lifted the weights between 15 and 25, but only a few, like me, would lift them this heavy, and then maybe not so many people using the 5 kilogram as well. All of these are examples of distributions, and in fact, they are examples of normal distributions, and they fit very well what we call a bell curve, because it looks a bit like a bell. Even more precisely, it looks even more like a e to the minus x squared kind of curve, but we'll get back to that in a second. What's going on? What other things are similar about them? I suppose that's the main thing, but they kind of have a symmetry going on about them then, don't they? A line of symmetry. Again, maybe not so much at this bottom left, but the other one's pretty good. Yes, there's a jump here, but it's pretty good symmetry. And actually, I just want to again talk about some of the graphs. So we've got IQ score. We've got most people score an IQ of 100. That's the definition of 100. If you're being sort of standard, and then you get some people above, and then some people like way above, some people below, and some people way below as well. Actually, it turns out that this kind of curve occurs in lots of different places. So if we look at the heights of men and women, this is some sort of sample. We've got frequency here. You can see like hundreds of people have been asked. Then you get some people that are a bit shorter, you get some people that are a bit taller, but on the whole, they seem to fit this same curve. The same with the men. Here we're looking at percent per pound against weights. I don't actually know what this quite is, to be honest. And the reason I put this one in there is because it doesn't quite fit a normal distribution, and actually there are some curves that you need to modify. They might have more of a tail in one direction than the other one. This is actually a different type of distribution, but it's kind of based on this normal distribution. And yeah, I think this one's great because it's like a real visual picture of a normal distribution. Maybe not, again, you can kind of see there's lots of, I wouldn't say this is grouped data, as you can see, and I'm fitting a continuous curve to it. And maybe there's not as many intervals here, but you can still see that you could roughly sort of fit this curve to it. So as I said, these are all normal distributions, arguably the most important distribution in statistics. I'm going to try and convince you a bit more why that's the case in a minute, but maybe I've already convinced you because of how you've seen it come up in two key places, or more than two key places. Because it appears naturally in many scenarios, that's why it's called normal. And if we just take a little history lesson before we get more onto this, actually this was first derived by De Moivre in 1733. He was doing some sort of gambling problem and it came out. Gauss did some key work on it in the 1800s, and actually you will see he has a lot of stuff, even though this was 60 years later. He did a lot of crucial work, got a lot of credit for it afterwards, and this type of curve is also known as a Gaussian. So a normal distribution, a Gaussian, a bell curve, these are all names for the same thing. It became known as a normal distribution from the 1870s, I think because it just occurred in so many places. They decided, yep, and maybe they found, I don't know for sure, but I think they found distributions that were maybe a bit more like this, and they wanted to give these a slightly different name, so they called the symmetric ones normal, and then other names for other ones. And a guy called, I think it's Pierre Laplace, he devised something called the central limit theorem, and that also really cemented why it's such an important distribution. I'm not really going to be talking about this much in this A level, but the central limit theorem is about taking samples and they themselves then follow a normal distribution, and Laplace showed that it would always be the case. So even if something doesn't follow a normal distribution, its sample if you take a look at the mean of the different samples, then it will follow a normal distribution. Anyway, that's quite vague, but it's also cemented how important the normal distribution is. Okay, so let's just take a little step further. So how do I get this continuous curve going on? I've got lots of bars at the moment. What's the process that's going on? And I'm going to talk through this briefly now. So we've got some histograms here, and you've studied histograms. You know, I hope, that the area of a histogram bar displays the frequency. So I've got the frequency density going on here. If I wanted to know the frequency, I would do the height times the base times the height. Now in this case, they've actually turned it into the relative frequency density. So I think they've done the frequency density and then divided by the number of people, which has essentially turned it into a probability distribution. Let me just talk a bit more about that. So because if you have a normal histogram and you might find that there's 80 people here, well, if you wanted the percentage, you would divide by the total number of people. That would tell you the percent. That is precisely what relative frequency density is. So we've got a histogram, but then we've divided by the total number of people. So now when I find this area, I'm actually finding not the number of people, but the proportion of people. Very similar quantity, but it's going to be more useful, in fact, because I don't want my histogram necessarily to depend on the number of people, so I can normalize them all, I suppose. I'm using the word normalize. I can make it also. I can turn it into a probability distribution anyway. Let's just say that. Let's think about what if I made the gaps a bit smaller. Instead of groups of 10, I went to groups of 5. Well, then I can see that I'm going to get lots of more bars, but I'm going to get like this kind of shape going on. It's going to become a bit less blocky and a bit more continuous. And if I had enough people in my sample, maybe I've got thousands of people in this sample, then I can keep doing it. And you can see how it's starting to form a continuous curve. So whilst we've got group data, it's looking more and more continuous. And if you kind of took it to the extreme and you just made it smaller and smaller and smaller, then you would get something a bit like this. So instead of relative frequency density, I'm writing probability density because now I'm looking at an actual continuous function. And there's two important things, actually, one that I've already said, but another important thing I'm going to talk about in a second. First is that the area underneath the whole thing is going to equal 1. Because we're basically dividing by the number of people here, but that's the definition in our normal distribution. We've just derived a probability distribution. What else is there? We have the mean. So the mean, because it's perfectly symmetrical, hopefully it makes sense that the mean is going to be going down through here. But there's something else quite important. The median is the middle point, and because it's perfectly symmetrical, actually the median is going to be here as well. Back to the mean, I think I've just glossed over this. The mean is sometimes given the symbol mu. So actually I'm saying here the mean height is 175. The median height is also 175, and guess what? The most common heights going on, although I don't have numbers, I've got probability density, you can see the highest probability is that it's its height 175. So in this distribution, the mode, median, and mean are all exactly the same. And then I'm going to come back to this in a second, but we get a variance or a standard deviation going on with this distribution as well. And that is what this last number is here. This is saying that X follows a normal distribution with mean 175 and standard deviation 12 or variance 12 squared. More on that another time, but I just thought I'd define that since it was there. So I've already kind of talked about this bit. I hope that you are happy from this start what a normal distribution is. And you might not know quite how we're going to do calculations with it yet, but that's okay. We've seen this function e to the minus x squared. We've seen that we can integrate it, more on that in a second. We've seen that it seems to crop up in different places. We haven't derived it. Okay, I'm not going to be doing that. There are videos out there that will derive it there of a higher level than we're going to go into here, but you can show, like de Moivre and Gauss and Laplace, that you can derive this distribution. We've seen what's going on, how the shape is formed, and I've also talked about the idea of a histogram and how I can derive it from that. So far, this lesson's pretty much been background about where the normal distribution came from, how it kind of arises, why it's important, and like why the shape is as it is. Because, well, for the rest of this lesson, we're going to look at something called the standard normal distribution, and this will make more sense when I cover general normal distributions with different means and standard deviations. But this is how we denote it. Z, we often use Z for the standard normal distribution. We say that it follows a normal distribution with mean. So that is mu, that is a parameter of our normal distribution, a bit like n is a parameter of the binomial. That was meant to be a mu, I'm just going to write that out again. And this here is actually the variance. So the variance is equal to 1, but in this case that also means that the standard deviation is equal to 1. And that's how we write it. And what the function looks like for this normal distribution is this thing here. Now I've got 2 points to make. Actually, this is not even on the specification to know the equation, but I think it's one of the most interesting things. So I've decided to spend some time on it and get into that kind of detail on it. And also, I don't know if you took a second glance at this, but where on earth has pi come from, you might be thinking. Well, it turns out that's what you need to use to make the area under this curve equal to 1. If you remember previously, I said that was the case, the area is equal to 1. You have to divide through by square root of pi and some other things to make it equal to 1. And I don't know about you, but that is, wow, what's going on there? In fact, you can show it's true, and I'm going to do this in a separate bonus video. It goes a bit, well, we're already going above the specification, but it goes well above the specification, but also I think it's absolutely fascinating. But essentially the result is, if you integrate e to the minus x squared between plus and minus infinity, then you get the square root of pi. These two numbers that appear in maths are interlinked through this. I'm not going to say anymore, get excited about it anymore in this video. I'm doing a separate video to derive that. But essentially, we have to divide by root pi. Now, where does the 2 come from? Well, that's just what we need to get the variance is equal to 1. So we end up having to divide by the 2 here and here as well. So the question is, how do we then work out probabilities? Well, this is the sort of thing we have to do. We have to do an integration. This is the difference, because now we're looking at a continuous distribution. Instead of like finding these different probability bars and adding them up, we do an integration. And one such integration, if you wanted to do the cumulative normal distribution, like not normal distribution, the cumulative probability, then this is what you'd write down. You do an integration from minus infinity, because this goes on forever. It might look like it's touching 0, but it's not. From minus infinity up to z, it'll be all of this area, and that would tell you the probability that z is less than or equal to z. This is given a special symbol called phi. It's actually capital Phi, because lowercase phi is that there. Now you might see this now and then, so I did want to raise it, but actually there's a function on your calculator because part of the reason why phi used to be used all the time is that there weren't calculators to do these kind of calculations. So if you wanted to do the probability that z was greater than little z, it would be 1 minus phi of z, because yeah, this and this are going to add to 1. And you could write probabilities all in terms of phi. It's less commonly used, well, it's not really used a lot in A-level maths now. But therefore, if we want to work out the probability that z lies between a and b, then you end up with this very similar integral, but with a and b in there. So what we are doing here is we've got a normal distribution. Actually, it's centered at 0. I don't know why I drew my axes like this. Let me do it once again, just like that. Okay, and now I'll have A, I'll have B, and I'm actually finding the area under my curve between A and B. A bit like we're doing with a histogram, essentially, but now it's a probability because the area is 1. It turns out that this is very hard to integrate. I'm not just going to say to you, yeah, integrate it, off you go, because as soon as you put a z squared in there, it's out the window. Whilst you might be able to integrate e to the minus z, you can't integrate e to the minus z squared. I've written it's very hard. It's actually impossible. It is not possible to find this integral in general. We can do it for this one up here where it's plus and minus infinity, and that is the beauty of that, to be honest. But in general, you just can't do it. So what we have to do is use our numerical methods of integration, which we've learned about, and we're ready to go. So let's give this a go then. Let's take our standard normal distribution and find the probability that z is between 1 and 2. How on earth do we do that? Well, we know we're doing an integral between 1 and 2. Again, actually, we're not going to be using that from here on. We've got our calculator to do it, but I want you to kind of realize that actually that is what you're doing integration. More on that in about a minute's time. Because what we do is we go to our calculator like we did with the binomial distribution, but here we go, you find the normal. And you actually never use normal PD. We'll come back to that in a bit. I know I'm saying this for about a lot of things, but we're going to use the normal CD button. And here it gives us a lower bound. That's going to be 1. It then gives us an upper bound. That's going to be 2. It's asking us for the standard deviation, which in this case is 1 because we're going with the standard normal. If we go down, it asks us for the mean. So it's preset as the standard normal distribution. And if we press equals, we get our answer 0.1359. I think I've worked to 4 decimal places throughout all of these, but that's our answer. That's our first ever calculation using a normal distribution. Or is it? Because when I asked you earlier on to use the trapezium rule for that function there, that was precisely what I was getting you to do. I asked you to use the trapezium rule, and you did your first calculation using the normal distribution, but the probability that z lies between 1 and 2. So we see it was 0.1366 here. Actually, the exact answer is 0.1359. Trapezium rule, yes, it's not perfect, but that's what was going on when you did that calculation. From now on, we use our calculator, but that's what your calculator's doing. It's just using, it's not using the trapezium rule with 4 intervals. It's using some other method. Okay. So now I've said that, I'm going to go through a few, but I want you to try this question to yourselves. Okay, let me talk through this one. If you press equals, you get back to the main menu, and then all you do is you replace your lower limit by 1.66, your upper limit by 1.86, and we get our answer, 0.9201. Okay, another calculation done. I should say, actually, I did give these little graphs, and I'm just going to shade them as I go, because I think it gives a good feel for what's going on. So we found that area, and now we found that area. Essentially, we're finding the probability in a normal distribution that, like you would, at random, whether you would lie in these intervals. Because I've not really talked about that at the moment, but it's a bit like when you're doing random trials and binomial, you could get a certain number of successes or failures. This is a normal distribution with a range of different values for z. And if we just picked one at random, you can see there's a higher probability that I'll be around here than out here. But if we picked one at random, there would be a 13.6% chance that it would be between 1 and 2. That is actually what's going on here. It will make more sense in lessons to come, I think, because we're just introducing it here. All right, I'm going to talk about number 3, because it's a bit different, isn't it? Because this time I don't have a lower limit. And that's because there is no lower limit. It's actually going to go on from minus infinity. If I was to sketch it on my graph, then it is all of this. And you might even say that it is phi of 1.64. Now what do we do then for our lower limits? Well, it's minus infinity, but there is no minus infinity button. So this is what we do. We just put in a large negative number. And you can see how quickly it goes to 0. Right, minus 99 is going to be enough. But I normally just go for it and I say, yeah, let's make it minus 9999 or something like that. Just really big negative number. And then 1.64. Okay, and that will sort it out. 0.9495. All right. I want you to pause the video and have a go at number 4 yourself. So the probability that Z is greater than 0.85. Well, for this, it's going to be very similar, but make 0.85 the lower limit. And now just put a load of 9s in. It doesn't have to be 9s, by the way. I'm just like, it just makes more sense to do 9999 rather than 8888. You could make it 10,000 if you wanted, but then you'd have to type in an extra digit. There's nothing special about that number. It's just big. 0.1977. There we go. Okay, another 2 to try. Please give them a go. For these, you should have got, I'm not going to go through them, you should have got this and this. And it would have been this area. And then this is quite a small part because it'll be this area here. All right, 2 more to go, and actually that is our lesson for today then. We're just introducing it. It's gonna make more and more sense the more lessons we do. What about this one? Well, the answer to this one you can actually do without a calculator because we've said that the median is the same as the mean and it's symmetrical. So actually this must be 0.5. If you put it in your calculator because that was your automatic response, that's absolutely fine. But I just wanted to point that out really, the fact that half of the values are below 0 for the standard normal and half are above. What about this last one, number 8? Well, let's go with it. Let's just see what our calculator says. 0.3 and 0.3. 0. Okay, what's going on there? How can the probability be 0? Well, that, to be honest, is not an oddity. That is a standard result of any continuous distribution. And it makes more sense if we return back to our starting formula for the probability. We've just worked out the probability that Z lies between 0.3 and 0.3. And when you put the same number into your integral, you always get 0. So from that point of view, it makes complete sense, I think. And you could replace this by A. Probability at any point is equal to 0. And remember, you're not, like the whole point really is that we were finding areas here, and now we're just finding a single line. So the result of a continuous distribution is, as absurd as this might sound, the probability of getting a single value is 0 anywhere you go. Throughout the entire space, the probability of me landing at a single value is 0. It only makes sense to look at an interval of values, and then suddenly the probability becomes a finite thing. So you might see the 0 instead as being an infinitesimal. It only makes sense to look at a range of values. If that doesn't make sense, well then think back to your histograms. When you did frequency of a histogram, you would have calculated a certain amount of it. If you made it infinitely small and said, I want the number of people with an age of exactly 15, let's say, then if you did that, you would have got 0 as well. So it's just something to be aware of. And it also brings one other fact in that maybe you thought about before, but this holds as well. The probability that A is less than Z is less than B is the same as the probability that A is less than or equal to Z, less than or equal to B. So for a continuous distribution, we do not have to distinguish between less than and less than or equal to. And that's a nice thing. For binomial, we obviously had to be more careful, but it didn't matter. I think I had less than for all of these, but I could have equally have put an equal sign in and they would have stayed exactly the same. Hopefully you're happy with those calculations. Even if it's not quite coming together, you're able to implement it with your calculator and it will continue to make sense. I've gone in quite very theoretical in today's lesson, like showing you where the function, like where the curve comes from, the fact that it is a function, the fact that we're doing an integration of it. I've used the trapezium rule and shown that it does actually work if we use our calculator. I've talked about the shape, and then I've talked about how it's essentially related to a histogram. And finally, we've looked at the formula of the standard normal. We've talked a little bit about the mean and the variance, but there's more to follow on that, and we've done our first calculations. More to follow, but well done on this start to what I think is quite a tricky topic when you first see it. Welcome to this bonus video. 10 cool points to you for giving it a watch. We, in this video, are going to integrate the following function, e to the minus x squared. Now I said that it is not possible to integrate this generally between two values, but it turns out it is possible, as weird as this might be, to integrate it over an infinite range. Okay, and actually that's the case for many integrals, but it's absolutely essential that we can work out this integral. And the reason, if you remember, is that we've got some sort of normal distribution, but we need the area to be 1. And if the area, so what do we have to do? We need to divide by whatever the actual value of this integral is, and that will make it equal to 1. So it's really important. Why is this integral so hard? Well, if we just think about a very similar integral, x e to the minus x squared, this is not so bad because you can solve this by inspection. If we differentiate e to the minus x squared, then I get minus 2x, I use the chain rule, minus 2x e to the minus x squared. That means if I integrate this thing here, then I'm going to get back to e to the minus x squared. I just need to then divide by this minus 2. It's going to be minus a half. We can deal with that, and that's great. But as soon as you get rid of the x, I need something that integrates to give e to the minus x squared. It just falls apart. And so that's what makes it so difficult, essentially. How are we going to do it then? Well, it's not at all obvious, let's say, and you just got to roll with it. I'm going to show you a method, and I have no idea who first came up with this, but it is remarkable. I'm going to call the integral I, and then I'm going to do something that you never, ever, ever do for integrals. I'm going to square it. So between minus infinity and plus infinity, I've now got the square of the integral. Why do that? Because now, although it's going to take a few steps to see why it's so useful, I'm going to split it up into two integrals. One in terms of x, and then a second one, which I am going to make in terms of a different variable. It's going to be e to the minus y squared with respect to y. That's okay. Yeah, I'm multiplying the integral by itself. What's wrong with integrating with respect to x and then with respect to y? Remember, I'm just getting a single number out of it. It's absolutely fine to do that. And here's so there's nothing actually off the A-level syllabus at this point. It might seem strange that we're doing this, but I can do it. This is the first bit that's maybe slightly cheeky, let's say. I can actually bring the integrals into a single one. So I can integrate with respect to x. I need to now label my limits because they're going to be next to each other. I can have the x and the y limits next to one another. And then I can have the two functions inside the two integrals. This is okay to do because they don't affect one another. It's a bit like moving a constant out of an integral. It's okay. I can't move that out of here because I'm integrating with respect to dy here. But I could move that one into here, that would be all right. Okay, that's a bit loose. I haven't really I haven't proven that or anything. I'm just asking you to, does it seem okay? I'm just asking you to trust me with it. It's not rigorous. And what we can then do is, because I'm multiplying two exponentials, I can actually bring it together as one exponential. So minus x squared minus y squared. And then I can do one other thing. I can factorize out the minus, and it becomes that there. Okay. This is all right so far. Whether how does this make things easier? Well, we need a little trick, and this is the remarkable. Once you see it once, I suppose you're like, oh yeah, I kind of see how it works, but I don't know how you would see it for the first time. But there we go. Right, when we have dx, it's an infinitesimal amount. If I then times it by an infinitesimal amount in another direction, I actually end up with an infinitesimal area. This thing can be seen as an area. And what I can do is, instead of using a Cartesian coordinate system where I go x along and y up, I can actually change my coordinate system. So I can pick a coordinates here, which is x, y. And then instead of saying I go along x and up y, I can define it using polar coordinates. You may have seen them, you may have not. And these are defined such that I'd measure the distance to the point, r. That's my parameter, one of my parameters. And then the angle that I turn from the x-axis. And I can, instead of using x and y, I can use r and theta, and I can, in this integral, I can change my coordinate system. If I want my dA, then this is how I do it, okay? I can actually get dA by thinking of an r and a theta, and then increasing my r to r plus dr, increasing my theta to d theta, and finding the value of this infinitesimal area. And it's actually going to be, the arc length is going to be r d theta, just like the arc length working in radians, when you have theta and r is s equals r theta. Not proven that here, but that is the case. So if I can work out that arc length, and then I can work out this distance, which is dr, it's just this extra distance, then I can kind of approximate it roughly as a rectangle, I suppose, a similar rectangle going on. And it's going to be r dr d theta. Now that was probably the least rigorous bit of this calculation, but again, this is fact, and there are more rigorous ways of proving it, but that's not for here. All I'm asking you to do is believe me, and then we can write down our next step. Now the thing is, I'm changing my coordinate system, so if I want to include all of space, I need to go not from r as minus infinity, because r is always, it can never be negative. It's actually going to be r is 0 to infinity. And then this theta, if I want to include all the space, is going to start at 0, go all the way around, so its maximum is going to be 2 pi. We're working in radians here. Now, there's a few things I've not yet said. I've not related r to x and y, but I can do that because I've got a triangle here. So actually, r squared is equal to x squared plus y squared. It's just Pythagoras' theorem. And just for interest, theta, or should I say tan theta, would equal the opposite, y, divided by x. We can do a transformation of coordinates. Now in my case, I don't need theta in there. I've just actually got a very simple thing, x squared plus y squared. I can change that to r squared. And then instead of dx dy, I can change that to r dr d theta. And this is where we take a little breath and just think, okay, somehow we've managed to introduce an r into this. And I said a minute ago that when we had an x there, it all worked out. So I'm going to delete this a little bit and carry on from here. So I want to link it to above. Now what I can do now is I can actually do the opposite of when I brought the integrals together, and I can separate them out again. I've got my r integral, but this is not dependent on theta, so I can write it here. And then I've got my theta integral, which is just with respect to theta. And that, or 1, I'm integrating 1 with respect to theta, you might see it as. And what this will become, if I work it out, will be theta, because if I integrate 1, I get theta, evaluated between 2 pi and 0, which is 2 pi minus 0, which is 2 pi. We're nearly there, I promise. This is going to therefore equal 2 pi times the integral from 0 to infinity r e to the minus r squared dr. And as I said before, that thing there, check it out, is actually minus a half e to the minus r squared. But it's going to be evaluated between 0 and infinity, and I still need to multiply by this 2 pi. Now in A-level maths, actually, they've taken this kind of thing off the syllabus, putting in an infinity. So again, it's going to be a little bit hand-wavy, but basically just imagine r being really, really big and seeing what happens. And if I make r really, really big, but it's e to the minus something really, really big, actually this term is just 0. Technically, we would substitute an a and then take the limit as a approaches infinity if you want to be rigorous, but you do get 0 coming out. And then we need to minus a half e to the 0. And that is just 2 pi times a half, or pi. And suddenly you see, actually I didn't really make a big deal of it, but yeah, the pi came into it at this point here. Like there's no mention of pi, and suddenly we turned it into a different coordinate system, and pi just naturally came out because of how it does with angles, essentially. And therefore, we're not quite done, because remember, that was equal to I squared, but therefore, this integral is the square root of that, which is the square root of pi. Now, are we done? We're pretty much done. But as you saw from the standard normal distribution, it didn't quite look like that, did it? It actually had x squared over 2 in it. So I'm going to do a substitution just to finish it off. Let x equal u over root 2. Why do this? Because that's going to mean that x squared is u squared over 2, and that's what I want. I want that in my power. So then dx by du is going to equal 1 over root 2. I'm not sure how you've been, how you would have been taught changing, doing a substitution, but I'm going to do like the cheeky way here and just write dx equals du over root 2, and then essentially I replace this dx and I replace this x, and I also see that the limits won't change, because as x goes to infinity, u will also be going to infinity. So I can therefore say that this thing now in terms of u will be minus u squared over 2 du over root 2, and that will equal the same as we had before, that root pi, and therefore if we multiply through by root 2, we see that this integral on the left is actually equal to this thing here. So if we want to construct our standard normal distribution such that it has an area of 1, we need to divide through by that, this 1 over root 2 pi, because then finally we'll get this. I can now change it maybe to a z, equal to 1. We've taken this curve that looks like this, and we've ensured that the area underneath is equal to 1.